Hi, this is Tim Malloy with video 3-3. This one's going to be very long, so I'm just going to jump straight into it. Problem 11 on 11E, by the way. Okay, so two long wires hang vertically. Wire 1, I'll zoom out so you can see my picture at the bottom. Sorry. Wire 1 carries an upward current of 2 amps. Wire 2, 20 centimeters to the right of wire 1, carries a downward current of 4.4 amps. A third wire, wire 3, is to be hung vertically and located such that when it carries a certain current, each wire experiences no net force of N equals 0. Alright, so I decided, well, first off, I just want to say this is part of my takeaway or reflection of the problem. Do problem number 9 first. You need good right-hand rule skills for this problem. I will go over the right-hand rule briefly, but honestly, I think that this is a higher level problem, so that type of knowledge should be expected. Okay, but going over the what is this? The setup, the picture. So yeah, we have a wire up. Here's that current. Wire down. Here's that current. Electric field at each point. We know by our curl rule that these wires are both have inward fields, inward magnetic fields. Hopefully, I don't confuse that with electric in this problem because I just slip up on my words sometimes. But anyways, inward on the area in between the wires, outward on the area outside. Again, that's just the curl rule. And here's that distance in between the wires. So okay, cool. Which way do forces point though? So remember that this is the right-hand rule, by the way. Again, I will briefly explain it. Which way is charge moving is our pointer finger. The magnetic field lines are what is that? The middle finger, and the force is our thumb. When when calculating for it, this will come in. I'm sorry, just when finding magnetic force, use magnetic field of the thing applying the force, and use the current direction of the thing receiving the force. I'll briefly demonstrate that with wire 1. So wire 1, when acting on wire 2, the field is into the page and the current is upwards. So you point your fingers like that, middle points into the page, point your finger upwards, and then am I doing this correctly? Okay, I'm sorry. So let's look at let's look at the force on wire 2. So again, by wire 1, which is applying the force, uh, the field points inwards, so we'll point our middle finger into the screen, and we'll have to flip our finger around so the current points downwards, and so that way we have F1, or the force pointing to the right. Okay, I just explained my own thing, and I didn't know how to do it, but anyways, I was able to figure it out. So anyways, that was the example I did for force by wire 1 on 2, and then you can also do the right-hand rule to find the force by 2 on 1. And then we come up with these two free body force diagrams. And I know that there's the third wire, but again, I just want to run through the setup because this is how I solve the problem. You got to take it in small steps. You got to understand what's going on before you start throwing in that third wire. We know that this magnetic force by wire 2 is greater than the one that wire 1 exerts, because the formula for magnetic magnetic field of a wire. Did I say that correctly? Yes, okay. We know that the magnetic field of a wire formula is this, and wire 2's current is greater than I1, and by the way, F equals, oh shoot, what does it equal? Let me scroll for a second. Okay, ILB. So obviously if you have a greater magnetic field, then your force will be greater. That's how we know that. Sorry, just wanted to make sure I didn't leave anything out. Okay, so looking back at the problem, we need a big force acting on wire 1 to make the net force 0. And then we just need a smaller one acting on wire 2 to make that net force 0. So I'm thinking, let me scroll back up here. we need a big push, again, a big push on 1, a small pull on 2. So that if we position a wire on the left of wire 1, then we can have that big push and we can have that smaller pull because look at the formula, greater distance, less field, okay? And so here's our wire 3 that we are going to place. Now, how did I know which way the current pointed? Well, I just used my right-hand rule and I played around with it a little bit. So you can see if I have it pointing downwards, which is the correct direction. Let's test the force on wire 1. So due to the curl right-hand rule, our field will point out of the page. And then, oh, look at that. The current of wire 1 is upwards. So we have our middle finger pointing at us, our pointer finger pointing upwards, and then that leaves our right finger, our thumb pointing to the right. So ding, 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 that is the push. And then I will not do it for wire 2, but same thing applies. Then you get that pull. And again, I will draw a real free body force diagram like I did for these in a minute. It's just still explaining what's going on. So our green magnetic force by wire 3. So wire 3 on wire 1 is greater than wire 3 on wire 2. That's like what I talked about again. When you have more distance, your magnetic field will be smaller. Smaller magnetic field, smaller force. Okay, good. All right. And let's just look back at the problem because I think that setup looks pretty good. Is this situation possible? Yes, you can balance the forces. Is it possible in more than one way? No, because of the current in the one wire is greater than the other. And now they want us to find position of wire 3 as well as direction of current. Well, we do know where we don't know this yet. Sorry, spoilers. But we do know that it is left of wire 1 and that it is downwards. Again, how did I figure that out? Well, I used my knowledge of forces to find where to place the wire, and then I tested a wire facing upwards and a wire facing downwards, and then whichever one gave me the push on wire 1 and a pull on wire 2 was the correct direction, which was downwards. Okay, setup is mostly done. Let's get to calculating. Note how forces are balanced, because that's given to us. That's what we want to find. Let's reserve wire 3. So wire 3 has a force by wire 1 and a force by wire 2 acting on it. Right-hand rule tells us that the force by wire 2 points right, and the force by wire 1 points left. Here is my free body force diagram. Again, balanced forces. Set them equal to each other. We put them in terms of current, length, and magnetic field. You know what, why don't I draw B1 and B2 for that? Because these lengths are the same. I believe we can assume that the lengths are infinite or the same. So we can cross them out. And then we plug in our magnetic field equation. And remember, we are using the magnetic field of the, give me a second. Use the magnetic field of the thing applying force. Does that make sense? Okay, so we're using our current of the force, and then, okay, I suppose when we calculate this, we use the current of the thing receiving the force. Doesn't matter, cancels out anyways. We have all these things that cancel out. And then for A1, I plugged in D, and then for A3, I plugged in D plus 0.2 M. Again, this is D plus 0.2 M. That makes sense. We're able to plug in current 1, current 2, which is given, and then we can solve for D, which is 16.7 centimeters, and again, it's positioned on the left. Now they want the current. Let's look at wire 1. Force by 2 pointing to the left, force by 3 pointing to the right. Here's a free body force diagram on a grid. Set them equal, put them current, length, magnetic field. Plug in this for magnetic field, our formula, and then cancel all that we can. For A2, we're going to put in 0.2 meters, because from 1 to 2, just that. And then from 3 to 1, it's just D. So we'll put in D there. We have a value for D now, which we solved for. Solve for I3, 3.67 amps, pointing downwards. Okay, so that is all done. That is all good. Everyone's happy. Takeaways is right-hand rule is king. And again, number 9 is good practice. And I have to play with the wire position and the direction again when setting up. And, that's just something you gotta do. If it didn't ask for like directions the current was facing, I just would have thrown wire. I just would have thrown wire 3 on the left and then gone with it because screw what direction current is as long as I can balance the forces, right? But they did ask for that, so we did have to do some guess and checking and find that current direction. Hopefully, you'll learn to notice little details like, I mean, honestly, I think most of us have enough force knowledge to understand that we gotta put it closer on one side, put the wire or position the wire on one side rather than the other. And my setup might be overkill, but it serves the tutorial. And I'm sure this video was very long and you enjoyed watching every single second of it. So thank you for watching, and that's all.